Welcome to Astronomy Daily, your regular dose of the latest cosmic happenings and stellar insights. I'm Anna, and we have an exciting lineup for you today, packed with fascinating developments from across the cosmos. First up, we'll be checking in on Australia's highly anticipated Eris 1 rocket, which has faced some recent setbacks. Then, we'll take a deep dive into the fascinating world of exoplanets, exploring how Saturn's moon, Titan, is becoming a crucial benchmark for understanding atmospheres far beyond our solar system. We also have a dual report on satellite news, covering a successful European weather satellite launch and the unfortunate loss of a critical methane tracking satellite. Finally, we'll journey to Mars, where NASA's Perseverance rover is hard at work, grinding into ancient rocks to uncover clues about the red planet's past habitability. So buckle up, because we're about to embark on an incredible journey through space news. Okay, let's talk about Gilmour Space's Eris 1 rocket. This is a really big deal for Australia, as it's set to be their very first orbital rocket. However, its debut launch has faced a few more hurdles, pushing back its highly anticipated liftoff. Most recently, Gilmour Space decided to stand down from its planned July 2nd launch, citing the need for a longer, more flexible launch window for our first test flight, while a new target date is expected to be announced next week. This isn't the first time the Eris 1 has encountered a delay. The rocket was initially ready to fly back in May, but that attempt was nixed due to an early trigger of the vehicle's fairing. For those unfamiliar, the fairing is the protective shell at the very top of the rocket that shields its payloads during launch. This particular setback wasn't due to Mother Nature, unlike an even earlier delay. What happened was that neighboring components created a feedback charge during a routine vehicle shutdown. This engaged the fairing's single-use deployment protocols, essentially ejecting the protective shell prematurely. Gilmour Space explained that while shutdowns are a normal part of launch operations, this specific issue hadn't appeared in previous tests because the fairing separation system is a single-use component, only activated when absolutely necessary to ensure its reliability and safety. It was quite an unexpected glitch. Prior to that May incident, Gilmour was actually prepared to launch Eris 1 as early as March, but that first attempt was prevented by Tropical Cyclone Alfred. So it's been a bit of a challenging start for their maiden flight, but the team is clearly dedicated to getting it right. Gilmour Space, founded by brothers Adam and James Gilmour in 2015, has steadily grown and now boasts over 200 employees, supporting their operations and their Bowen Orbital Spaceport in Queensland. The Eris 1 itself is a modest but capable rocket, standing 82 feet or 25 meters tall. It's designed to launch payloads of up to 474 pounds or 215 kilograms into sun-synchronous orbits. This debut mission, named Test Flight 1, is the first of several planned flights as Gilmour Space works to qualify the new vehicle's various systems. Despite the setbacks, the founders of Gilmour Space maintain a very realistic and practical view of their expectations for this first flight. They've emphasized that any measure of success will be considered a win. As they put it in a press release earlier this year, whether we make it off the pad, reach max Q, or get all the way to space, what's important is that every second of flight will deliver valuable data that will improve our rocket's reliability and performance for future launches. This approach highlights their commitment to learning and iterative improvement, which is crucial in the challenging world of rocket development. It's also worth noting that the upcoming launch, whenever it happens, won't be streamed live. However, Gilmour Space has committed to providing updates through their social media channels, so we can all follow along with their progress there. We'll certainly keep you updated on the Eris 1's next launch attempt here on Astronomy Daily. Moving from rockets to research, let's turn our gaze to a fascinating new study that suggests one of our own solar system's moons, Saturn's Titan, could hold the key to understanding alien worlds light years away. The NASA ESA Cassini-Huygens mission, which explored Saturn and its moons from 2004 to 2017, provided incredible data, especially on Titan. The probe closely examined Titan, even deploying the Huygens lander to its surface, revealing insights into its atmosphere, methane cycle, and rich prebiotic environment. These findings, which led to speculation about methanogenic life in Titan's vast methane lakes, are now being leveraged for exoplanet research. With next-generation observatories like the James Webb Space Telescope, or JWST, we're moving from simply discovering exoplanets to deeply characterizing their atmospheres. According to this new study, Cassini's detailed examinations of Titan's atmosphere can inform these attempts, serving as an aspirational study to help astronomers anticipate and overcome interpretation difficulties. This significant research was led by Prajwal Nirala, a graduate student at MIT, and co-author Juliette DeWitt, an associate professor at MIT and leader of its Disruptive Planet Group. Their paper, currently under review for Astronomy and Astrophysics, consulted data from Cassini's Visual and Infrared Mapping Spectrometer, or VIMS. VIMS conducted high-fidelity observations of Titan using solar occultations, where sunlight passing through an atmosphere is analyzed to detect chemical signatures. These observations confirm Titan's atmosphere is 95% nitrogen and about 5% methane, with trace hydrocarbons. The data also revealed Titan's methane cycle, similar to Earth's water cycle, with liquid methane forming clouds and raining onto the surface. As Nirala and DeWitt explained, the Cassini mission demonstrated how challenging it can be to identify molecules in atmospheres because different chemicals can have similar absorption features. This can lead to mischaracterization, with drastic implications for determining a planet's habitability. Their study's primary focus was to leverage Titan's precise transmission spectrum and our existing knowledge of its atmosphere to investigate the strengths and limitations of exoplanet atmospheric retrievals, specifically assessing if misinterpretation impacts only spectroscopic features or biases other atmospheric properties. Exoplanet atmosphere characterization has advanced significantly. Previously, astronomers relied on transmission spectra during planetary transits. Thanks to Webb, direct imaging of exoplanets based on reflected light is now possible, a monumental step forward. The core challenge remains properly identifying chemical spectra to determine biosignatures. The team used the publicly available Tierra model, a one-dimensional spectroscopy code. In this study, they expanded the model to include a wider range of molecules and account for the similarity of their signatures based on existing astronomical data. Their findings revealed that spectral signatures can not only be easily misidentified, but such misidentification can also bias other atmospheric parameters, like temperature. This highlights the crucial connection between detection and retrieval that wasn't previously fully appreciated. What researchers choose as detectable significantly affects their atmospheric derivations. Another key insight relates to identifying the dominant background gas in an exoplanet's atmosphere, even if it lacks strong absorption features, like nitrogen. This is crucial for understanding the atmospheric chemistry and provides essential context for interpreting trace gases, including potential biosignatures. As the exoplanet census grows, the search for habitable planets is entering a sophisticated phase. Webb has already shown its ability to characterize exoplanet atmospheres and make direct detections, like TWA-7. Soon, Webb will be joined by the Nancy Grace Roman Space Telescope and powerful ground-based observatories like the Extremely Large Telescope, Giant Magellan Telescope, and 30-meter telescope. These will enable more direct imaging and detailed characterizations. The ability to properly identify potential biosignatures is indispensable for finding an Earth 2.0 quote or other habitable exoplanets. Nirala and DeWitt believe their work will help the community transition into this new era of information-rich data. They emphasize the need to ask, what can we reliably say from this data? They break this down further. What can we reliably say given our current models? And what could we say if we had perfect models? The first helps account for current limitations where models, not data quality, are bottlenecks. Not accounting for model-induced noise leads to overconfidence. The second question identifies dominant model limitations, showcasing the depth of science achievable with targeted upgrades. It's a call to refine our tools as much as our observations. Now, let's pivot from looking far beyond our solar system to the instruments orbiting much closer to home, with some mixed news from the satellite world. On one hand, there's been a successful launch that will aid in environmental monitoring. SpaceX's Falcon 9 recently launched a European satellite designed with a dual mission to collect vital weather data and to monitor atmospheric pollution. This successful deployment adds to our growing capabilities to keep an eye on our planet's changing climate from above. However, on the other side of the coin, we've received some disheartening news about another crucial satellite. MethaneSat, which was anticipated to revolutionize our view of methane emissions, has unexpectedly lost power less than 1 year and one half after its launch. According to a statement from the Environmental Defense Fund, the nonprofit organization that launched and operated the satellite, MethaneSat, is likely not recoverable. This loss is a significant setback for global efforts to track and curb methane emissions, which are a major contributor to the rise in global temperatures. Launched in March 2024, MethaneSat joined a growing constellation of satellites dedicated to detecting invisible methane emissions from key sources like oil and gas wells, livestock, landfills, and wetlands. While other satellites focused on individual sources or broad regions, MethaneSat was uniquely designed to detect methane at a middle scale, making it ideal for spotting emissions from oil and gas production. The satellite, which cost nearly $100 million to build and launch, began collecting data in June of last year and released its first detections of methane from oil and gas basins in November 2024. Researchers were actively working on automating data processing to deliver near real-time information on emissions. The Environmental Defense Fund reported losing contact with the satellite on June 20th, and after exhausting all options to restore communications, they confirmed the power loss. The MethaneSat team is still investigating the exact cause of the malfunction. They will continue to share the valuable data the satellite managed to collect before its power failure, along with the algorithms developed to analyze it. While it's a significant blow, the Environmental Defense Fund hasn't ruled out launching another satellite in the future to pick up where MethaneSat left off. From satellites orbiting Earth, let's now journey to Mars, where NASA's Perseverance rover is literally digging deeper into the red planet's geological past. The rover has shifted its focus from primarily scouting and sampling to more detailed on-site science, beginning to grind into Martian rock surfaces to expose material that could hold crucial clues to the planet's ancient environment and potential habitability. Earlier this month, Perseverance used its abrasion tool to scrape away the top layer of a rocky Martian outcrop it affectionately nicknamed Gilmour. This procedure, which combines mechanical grinding with a gas blast cleaning, reveals a fresh surface for close-up analysis. The goal is to study rock interiors that haven't been altered by billions of years of wind, radiation, or dust. Interestingly, Gilmour was a weird, uncooperative rock, according to Ken Farley, Perseverance's deputy project scientist. He explained that visually it looked promising for a good abrasion and possibly sample collection. However, during the process, it vibrated excessively and small chunks broke off. Fortunately, the team managed to get just deep enough below the surface to move forward with their analysis. Perseverance employs an advanced abrading bit and a gaseous dust removal tool, or GDRT, which applies 5 puffs of nitrogen to clear samples. This method poses less risk of contamination compared to earlier rovers that used brushes to sweep debris away. Once an abrasion is complete, Perseverance's sophisticated science instruments are deployed to investigate the exposed rock. The rover's Watson imager, which stands for Wide-Angle Topographic Sensor for Operations and Engineering, snaps detailed close-up photos. Its SuperCam then uses laser pulses to analyze the composition of vaporized material with one spectrometer and studies visible and infrared light reflected from the freshly exposed surface with another. The initial findings from Gilmour are already revealing fascinating insights. The tailings, or abraded debris, showed that this rock contains clay minerals, which are composed of water as hydroxide molecules bound with iron and magnesium. This composition is relatively typical of ancient Mars clay minerals. The abrasion spectra further provided the chemical composition of the rock, showing enhancements in iron and magnesium. Perseverance also relies on its Sherlock and Pixel instruments, which are designed to scan habitable environments with Raman and luminescence for organics and chemicals, and Planetary Instrument for X-ray lithochemistry, respectively. These tools help determine mineral content, chemical composition, and potential signs of past water activity or even microbial life. Not only did they confirm the presence of more clay, but they also detected feldspar, a mineral common in Earth's crust, the Moon, and other rocky planets. Crucially, the team also found manganese hydroxide in the observed specimens for the very first time. This work is being carried out in Mars' Jezero crater, a vast basin spanning 28 miles wide that once hosted a river delta and a lake. Scientists believe this region contains some of the best preserved records of Mars's wet past, making it a prime location to search for biosignatures or indicators of ancient life. Gilmour marks the 30th Martian rock that Perseverance has studied in such fine detail. The data being obtained from rocks like Gilmour is invaluable for future missions, providing a much clearer idea of what types of rocks can be easily traversed, sampled, or even used as construction material for habitats. Perseverance is also continuing to collect rock core samples, sealing them in tubes for a possible future return to Earth through the planned Mars Sample Return campaign. Although it's worth noting that the recently released fiscal year 2026 NASA budget proposal from the Trump administration suggests cutting the Mars Sample Return program altogether, highlighting ongoing uncertainties for this ambitious endeavor. That brings us to the end of another captivating episode of Astronomy Daily. We've covered some truly exciting ground today, from the ongoing saga of Gilmour Space's Eris 1 rocket and its journey towards launch, to how Saturn's moon Titan is helping us decode the mysteries of exoplanet atmospheres. We also discussed the latest in Earth-orbiting satellites, including a successful weather satellite launch and the unfortunate loss of the crucial MethaneSat, before taking a deep dive into Mars with the Perseverance rover's fascinating discoveries in the Jezero crater. Thank you for joining me, Anna, on this celestial journey through the latest in space news. If you want to dive deeper into any of these stories or catch up on previous episodes, be sure to visit our website at astronomydaily.io. While you're there, you can sign up for our free daily newsletter to get all the updates delivered straight to your inbox. And don't forget to subscribe to Astronomy Daily on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts so you never miss an episode. Until next time, keep looking up.